All right, we're going to do some projectiles problem solving. I want to refresh your memory about how we did regular kinematics problem solving. This is not all that much different at all. It has a very definite routine to it, and there are not a lot of tricks or tips I have to give you really, because it's pretty simple compared to what we've been doing. So I want you to imagine you've got a problem that's assigned, and it says that there's a projectile and it's launched off the edge of this table or whatever, and it's launched with some initial speed. Let's say it's 5 meters per second. Okay? And in the problem, it'll tell you generally how high it's off the ground. So let's say the table is 0.8 meters off the ground. And generally, often, the question is going to be, where does it hit the ground? What's its range? So what we're looking for is, what is this distance here? And you want to label, the given information on the diagram, but because most of our projectiles problem solving are so similar, it's not very difficult to get into a very nice routine in terms of how to solve these problems. Now, if you remember from the previous lesson, we already said that all projectiles have, this is true for all of them. So this will never change. This is independent of how it's thrown, what angle it's thrown. None of that matters. This is always true. So you can just put that in right away. And because it's so similar, and there's also a lot of information, we're going to organize it a little differently. Instead of labeling it on the diagram, besides what's all this stuff, we're going to make a little chart. I don't know if you remember from when we did kinematics, we always labeled V initial, V final, A, delta D, and delta T. Now, I set this up in a particular way, and I'm going to explain why in a moment. So in projectiles, because there's 2 dimensions, we have to have 2 columns, not just one. We're going to have the Y component and the X component. The word component just means part, right? So we have those 2 different axes that we were talking about here, the Y and the X. So we need to have 2 parts because their vectors and direction does matter. Time, however, is scalar. So the time is going to be the same regardless of what axis you're on. So once you find it in one component, that's the only one that will share information. But you're not allowed to let things bleed over. You have to choose from this or from that. And I'll explain that as we go. So let's solve this problem. What we're looking for is we're going to find this range. So how do we do that? Let's fill out the givens first. First of all, we know that if this is a horizontal launch, which you'd have to be told, a horizontal launch tells you that the initial angle, so theta initial is equal to 0, and what that tells you is that Vy initial is equal to 0. There is no motion up and down. So that's something you need to know that's implied by the words horizontal launch. This 5 meters per second is the X component of velocity, so you put that in. We don't know the final velocities, but we do know that since acceleration is 0 on the X and it's moving at constant speed, then final velocity on the X has to always be 5, has to be the same. This is 0 and negative 9.8. Notice I'm putting units on my givens. This is what we're looking for, so I'm going to put a question mark because I know I want to find dx. I want to find that x displacement. But the y I know, I'm falling 0.8 meters. So how do I show falling? Well, that's a negative sign because I'm moving down 0.8. I don't know the time. All right, so that's my chart. And then what do I do with this given information? Well, I want to find this, but I can't do it until I know what time is. So I'm going to need to find time using my y. So I'm going to find this first. Once I do that, I'm going to put that here, and then I'll have enough information to solve. Now, what equations am I solving with? Well, we're going to use our kinematics equation. So we've got V final equals V initial plus AT. V final squared equals V initial squared plus 2A delta D. We've got delta D equals v initial t plus 1/2 at squared, and this one. So these are our different equations that we've got. Notice they're the same exact ones. They're our kinematics equations that we used at the beginning of the year and have been using on and off all year long. However, you can only use one of these at a time. And I'll tell you, the most common one that you're going to find you use is this one. This comes up the most out of everything. Why? Because acceleration is always given. We generally are going to use one that has acceleration. We're almost always given the initial velocity. So that's pretty frequently what we do. And if you look, we have v initial on the y. We've got v initial, acceleration, and delta d, and we need time. So that means that's exactly the equation we're going to use. So we're going to do it on the y-axis only. So delta d is negative 0.8. Initial velocity is 0, so that term drops out. This is negative 9.8. So now I can solve for time. Take out the calculator. Let's be 0.8. Oops. We're going to do, sorry, having calculator problems here. Negative 0.8 divided by, that's negative 4.9, half of 9.8. You do this often enough, you'll know that by heart too. And then take the square root. And it comes up to be 0.40 seconds is your time. So that goes in here, which means it goes in here. Now I've got, so you might ask, well, why couldn't I just use v initial, v final to find, and acceleration to find displacement? Well, if you have these three, right, I mean, if you look at these variables, that would mean I'd have to use this equation. So I put 5 here and 5 here and 0 there. The 0 would make this term go to 0, drop out, and you'd have 5 squared equals 5 squared, which is not useful. So on the x-axis now, we actually have v initial, acceleration, we want delta d, and we have time. So it's going to be the same exact equation, but now we're going to apply it to the x-axis. So we've got delta dx, which we're looking for. V initial is 5, time is 0.4, acceleration is 0, time is 0.4 again. This term drops out because acceleration is 0, and you get delta d equals, what is that? 2, 5 times 0.4. It's 2 meters. And that's how you solve a typical problem for hang time and range.